All right, y'all. Today I guess in this video, we're going to be going over RC load half-wave rectifiers. And, this problem is a little bit difficult, mostly because of the equations that you're going to have to use. But once you have these equations on your crib sheet, it's more of a kind of just um, theory check. If he asks for any theory, of course. But if not, you can kind of fly by in this case. So, in this problem, we have an RC load, and remember, diodes in this class, or transistors, are also going to be in saturation or cutoff, so they're going to be acting as switches. They have no voltage drop across them unless otherwise specified. In this case, since this is a short circuit, only for positive, the positive side, that's what a half-wave rectifier is, then what do we notice? Well, we know the voltage at this point is going to be Vs. Vm is actually Vrms times the square root of 2. So it's equal to 120 square root of 2 is equal to 170 volts, right? That's Vm. So now we have an RC filter on the outside here. And now we can kind of get started. With this problem. So what is this question even asking us? Part A, it says determine the value of the filter capacitor, which is this C value here, to keep the peak-to-peak ripple across the load to less than 2 volts. So peak-to-peak is going to be delta V, delta VO, right? You're changing VO to be less than 2 volts. So there are some assumptions that you can make in RC, rectifiers. One of them being you can use a different equation to find your capacitor or capacitance or resistance given that delta VO over Vm is less than or equal to 0.04. So let's check this. Delta VO over Vm is going to be equal to, we can let delta VO equal 2 volts and divide it by 170 because we found this earlier. And we get it's about 0.012. Well, for me looking at this is much less than 0.04. 0.012 is less than 0.04. That means we can use this equation. The ripple is going to be equal to Vm over F frequency R capacitance. And we're looking for C in capacitance. So C is going to be equal to Vm over frequency resistance times the ripple. We know Vm. We know frequency is in the question 120 hertz. We know the resistance 750 ohms. And we know the ripple is 2. Solving for this, we get it's about 943 microfarads. So that's part A. Part B is going to ask us for the peak and average values of the diode current using the filter capacitor we found just now in part A. Now, for part B, again, we're finding the currents, the peak and average. So ID, we're looking for ID. We'll solve for this. Now, ID might be a little weird, mostly because you have a resistance and a capacitance. You have two separate currents, right? You have IC and IR. Now, what do we know about IC and what do we know about IR? Well, in the question here, it actually says IR can be approximated to be Vm over R. So IR is equal to Vm over R. And IC, if we use the relationship between voltage and current for capacitors, this is IC is equal to C dVc of t divided by t, or with respect to time. Take the derivative of voltage with respect to time times the capacitance. We know C, 943 microfarads, and we know Vc of t is actually Vs, right? The voltage across the capacitor is Vs. So what is this? This is C, the derivative of Vs of t divided by dt. In our case, that shouldn't be too bad. But we have IR and IC. What do we know about ID? If we do a KCL at this node that we have highlighted here, ID is going to be equal to IR plus IC. Using this relationship, and we know what IR and IC are, we can kind of solve for this pretty quickly. ID is equal to IR plus IC, and it's going to be 0, I guess 0 elsewhere. But where is elsewhere? Well, let's scroll up a little bit. It says IR is equal to Vm over R when alpha is less than or equal to omega t is less than theta. So that's what we're going to write here. Less than or equal to omega t is less than theta. And I assume it's going to be elsewhere, it's going to be 0. Now I'm going to draw this small graph for you so you can understand this kind of concept. So we have our sine wave here for 2 periods. Good enough. And what we're going to do is in our first period, which is 0 to 2 pi here, we're going to have this firing angle. So here we're at our maximum, which is what? Pi over 2. And then there's going to be a firing angle at which the rectifier will control this angle. This is going to be your theta value, at which the rectifier will cause your voltage to, instead of going down, create some sort of DC value. And we're trying to make this value hit a value on the second period, which is going to be 4 pi, right? This is going to be from 2 pi, and then it's going to be 4 pi. That doesn't mean the distance is 4 pi. I can rewrite this as 2 pi, actually. But this will be the first, and this will be the second period. That rectified wave here will hit the second period at an angle called the extinction angle. It's called 2 pi plus alpha. Now, you want alpha to be as close to theta as possible. This being because if theta is equal to, let's say, 91 degrees, because pi over 2 is 90, we want it to be 1 degree after, sure, whatever, right? And we let alpha equal 91 degrees, where is that? That's equal to where? That's equal to way over here, right? Very close. It's going to be essentially a ripple of what? 0. You're going to have 0 ripple. And that means 0 losses. You want no losses, right? I know I don't want any losses. So you want this to be the exact same. But in reality, it's not going to be the same. A lot of the times, you're going to have your alpha value be way over here, and your ripple is going to be so large, right? Your alpha value now is here, and it's less than theta. It's going to be very close to 2 pi. So alpha is going to be equal to something like 20. This distance between the max and the value that you have is going to be your delta V0. That is your ripple. You want it to be less than 2 volts, meaning you want it to be as flat as possible. Anyways, now that we've gotten that out of the way, we can now start solving, but now we need to find out what alpha is, the extinction angle. Alpha is going to be equal to the sine inverse of 1 minus the ripple divided by the amplitude. And this is equal to about 81.2 degrees. So to the left of your maximum, which is where we have it actually. And now we need to find out what theta is. Theta is going to be equal to negative tangent inverse of omega RC. This is going to be plus 180 degrees. And this is going to be equal to 90.1 degrees, not percent, degrees. And now, IC, what is IC? Just like we said up here, IC is equal to C times the derivative of the input wave. So IC is going to be equal to C times Vm sine omega t. This is given from the, problem, right? The derivative of this. And so then the derivative of this is CVM, derivative of omega t with respect to t is omega, derivative of sine is cosine, not so sine, cosine of omega t. So now you have your current equation for IC. Now you can rewrite ID in terms of IR plus IC. And now you have these values. So you have CVM omega cosine of omega t plus the IR value, which is VM over R, for when alpha is less than or equal to omega is less than theta, and 0 everywhere else. Theta less than or equal to omega t is less than 2 pi. So that's for ID. Now what about, let's see here, it also asks the peak, right? So we just found ID. This is the current values, but when does it peak? When should it peak? Well, let's find out. What value here, if we have a cosine, might it peak at? Will it peak at closer to 90? Think about it in terms of, just regular things going on. Just regular unit circle. Cosine of 90 is equal to what? 0. We don't want it to be close to 90. We want it to be the furthest away from 90 as possible. So it's actually going to peak at alpha, because alpha is the furthest away from 90. So what we can then do is say I peak at alpha, right? Because it's the furthest away from 90. Thus, ID peak is going to be equal to CVM omega cosine of theta, or alpha, sorry, plus VM over R. And this is going to be equal to 170, which is your VM, divided by 750, plus your capacitance value that we found earlier, 943 microfarads, times VM, 170, times omega, 2 pi times 120, cosine of alpha, or 81.2 degrees. And what we get is ID peak is going to be equal to about 18.7 amps. So hopefully right now you're understanding why we used alpha instead of theta. We can't say cosine of 90 is anything greater than very close to 0, right? So we want to get the furthest away from 0, and alpha is the furthest away from 0, since omega t is between alpha and theta. Now, it also asks us for the average value. We have the peak value. Can we use it to find the average value? In this case, we can't exactly or straightforward, solve for it using the peak value, but we know what is average value. This goes for anything. Average value for voltage, current, power. Average value is equal to 1 over the time period divided by 0 to whatever it is, right, of the instantaneous value with respect to t. Do we have the instantaneous or a function for instantaneous current? Well, yeah, we do. We have this here, ID of t. We found the peak current at some time or at some angle, so why not find the average value? So this should work. What is the period over which ID can, exist? Well, we do 1 over 2 pi, the integral over alpha and theta. Why alpha and theta? Well, that's going to be the same thing here. Theta and alpha, these are your bounds. 1 over 2 pi because we have a cosine. or a sinusoidal. And that won't change, by the way. This won't change unless in a specific equation they use 1 over pi. Sometimes they do. Then you use 1 over 2 pi. These bounds will change depending on what your bounds are for the problem. Anyways, now we plug in I d of t for when omega t is between theta and alpha. And this is d omega t. So plugging this in, this part is now going to be Vm over R plus omega c Vm cosine of omega t. I'm not going to do all the work here. I'm just going to give you the answer. And what we get here is about 0.232 amps. And this is your average current. I put a line for average. 0.232 amps equals 232 milliamp. And that's your answer. So hopefully this problem, was okay. If you really want to figure out why this works, you do have to understand this graph here. If you don't understand the graph, that's totally fine. You don't need to, understand the graph to get 100 or pass the exam. Just know the equations to use and when to use them. In the crib sheet, they should all be there. Some of them are a little bit more intuition, but most of them aren't. They're explicitly stated out for you. So hopefully y'all can understand this. If y'all have any questions, please let me know. You can reach out to me. Just message me however y'all want. If y'all have any recommendations for specific problems, please let me know so I can do them. But yeah, thank y'all. I'll see y'all on the next one.